I have here some data from an experiment used to calculate the value for Planck's constant. It was one done with coloured LEDs, and what we looked at here was the threshold voltage when the LED initially turned on and how that's related to the wavelength. Now with the LEDs used, these were the colours of LED, and according to the manufacturers this was the wavelength that LED corresponded to. We also then had the threshold voltage, we've got that measured in volts there, and the first thing we're going to do in order to get a graph like this where we can use the straight line and the gradient in order to find the value of Planck's constant is we need to look at values of 1 divided by the wavelength. So we can do that fairly simply just by taking this value here. That's actually given to us in nanometers, so that's going to be 10 to the minus 9 meters, and we can see for the first one we've got a very, very large number. But in the table here, I'm going to write down the data times 10 to the 6. So effectively, we're going to take that number, divide by 1,000,000, and then the first one is equal to 1.58. And we're going to do that for all of the data in that table. So here's the data all calculated, and we can see as we have a higher threshold voltage, we've got a higher value for 1 over lambda. So what we can now do is plot that on a graph. And so this is what it looks like. We've got the threshold voltage on the y-axis and we've got 1 over lambda on the x-axis. And also because of the data that we took from that experiment, we don't go back to the origin with these axes. So we're now going to put in a line of best fit, so an approximately equal number of points above and below the line. I think something like that is suitable. And so now I've got that straight line there, we can work out the gradient. So I'm just going to do my working out here. So the gradient is equal to the change in y divided by the change in x value. The y value, and looking at this, that's about 3.03. Take away this point down here, which is equal to 1.90. And on the x, it goes up to 2.45. Take away this value down here, which is 1.51, which equals 1.202. Okay, now what we saw over here, and that just reminded us, is that if V is equal to hc over E times 1 over lambda, that means the gradient is equal to hc over E. So we can find a value for h by multiplying the gradient by the elementary charge and dividing by the speed of light. So h is going to be the value for the gradient, which is 1.202. But of course this is the value for the gradient for this line here, but what we really have is 2.45 minus 1.51 times 10 to the 6. So that means the value for the gradient is really equal to 1.202 times 10 to the minus 6. We're going to multiply that by the elementary charge, so that's 1.60 times 10 to the minus 19, and divide that by the speed of light, 3.00 times 10 to the 8. And because we're multiplying a small number by another small number and dividing by a large number, we're going to get a very small number, which we do. We actually get an answer equal to 6.411 times 10 to the minus 34. So really, I think by looking at the graph that I've plotted, even though we knew some of the raw data to 3 significant figures, there's still a bit of uncertainty about the exact wavelength of light given out by that particular diode. We can probably justifiably give this to 2 significant figures. So this is 6.4 times 10 to the minus 34, and the units for that would be joule seconds. And of course what you can then do is compare your answer that you've got to the known accepted value, and that means you can really then start to think about how accurate your experiment is. Where were there sources of error? Was it in actually detecting when the current started going through the LED or when the light was first being emitted? Or maybe there's an error, in this case maybe in the manufacturer's number that they've quoted for maybe the average colour of light given off by those LEDs. Anyway, that was an approach where what you can do is look at the threshold voltage, you can look at the wavelength of the LED, and then you can use that, plot some data in order to find the value for Planck's constant.